Yes. We see it. You're good to go. I guess a little bit intro of like what stood out about this, like why you picked this paper would be great. My context would be Show-O, the original show, is from this guy, Mike Jung Show, the last author, who is a professor at NUS. And obviously, as a Singaporean, it stands out to me that some Singaporean guy who like with no prior name came out with this like really interesting multimodal LLM. And so I got very excited about it like a year or so ago when it first came out, the original paper. And then I did not see Show-O2, so this is new to me.
Yeah, I think, thank you for sharing. The reason why I select this paper is because I'm quite interested in this year's New York IPS. And I found this paper in the New York IPS paper list. And I found like Show-O2. And I'm interested in native unified multimodal models. So I think like to unifying things together is something interesting to me. So like I picked this paper. Okay, so yeah, shall I get started?
Sure.
Okay, great. So this paper, there are three main important parts. The first one is the abstract. So like the TLDR, what are some core concepts about this paper and the abstract? And the second one, I think, is mechanism. So there are mainly three layers of how the model works. And in addition, there is also some math formulas that explain the underlying mechanisms of the model. And the second one, and the third one is about discussion parts. So because I feel like it fills a gap of the unified multimodal models in 2025 because there is usually a trade-off between the understanding and generation and also between the language knowledge and the visual part. So this Show-O2 tackles this part, these two trade-offs in a quite cost-effective way because in its key findings, it also tells the readers that, okay, it has two versions of Show-O2. The first one is 1.5 billion tokens. The second one is 7 billion tokens. And these billion, for example, the 1.5 billion tokens compared to models like MU3 and also like other existing models, like have tokens beyond 6 billions, it actually outperforms them on certain benchmarks such as MMLU. And but despite of filling the gap, it also discussed two of its main limitations and points out to some future prospects. And these are the three main parts. And I feel like what intrigues me, apart from the neural IPS, is also it helps fill the gap. So about the abstract, I think the author makes it quite clear. So it is built upon a 3D causal variational autoencoder space. So it actually used a dual path. I think it is very interesting. So it has a spatial temporal fusion, helps to enable scalability across image and video modalities while ensuring effective multimodal understanding and generation. So in the later parts, we'll go to a picture, this picture, which tackles how the model works and also an example of the output. And it uses a two-stage pipeline as well as a dual path architecture to support the model. So for the introduction, I think we'll go through this very quickly. It basically tells us what have been achieved by the large language models and also what have not been achieved. So I think we can go to this table first. In the unified multimodal models, we'll just call it UMM for like to make everything easier. So there are two things. The first one is a unified and generative representation, and the second one is a type of unified modeling. So we can see Show-O2, which is here, this one. It has unified and it supports video and it is of the unified type of unified model, native type of unified modeling instead of the Taylor models. So actually, I think that it is quite useful because it both supports a video and it is a unified model. And after that, the author discusses about what they did. So they have the key concepts of 3D causal variational autoencoder space. I think for 3D, it has a spatial, which has the X and Y axis, and it has the temporal, which is, we can call it the T axis. So it is the 3-dimensional. And for the causal, it has the logic. So it supports the order of the model. After that, it is a two-stage training pipeline. When I was reading the paper, I really loved this concept because compared to existing models where some of the language knowledge can have the risk of being diluted if we enhance the quality of the image generation, the Show-O2 helps to preserve the language knowledge by having two paths. The first one is a semantic layer, and the second one is it can deal with the details and the texture of the image. So it can to discriminate between the different words' meanings. It can understand the grammar as well as the meaning of the words. And at the same time, it can help to increase the quality of the video and the image. So the second part is a related work. This part is help us to provide a holistic picture of the current UMM and the large multimodal models. I think the gap for LMM it has utilized image text aligned visual features in terms of performance. So basically, I think it means the image text part is not that good. So it wants to go beyond this pace to having a model that can deal with both the performance of the image and also the performance of the language knowledge. And the second one is the visual generative models. So it used two types of models. The first one is diffusion, and the second one is the AR modeling. And here comes the UMM, which is the main character of this paper. So it aims to integrate the capabilities into a single model through AR or diffusion modeling or both. So I think the very important part layers really called VA. So we can for example, we are giving a prompt to our model. For example, we say, what's written on this image? And we can ask the model to use any type of language to answer. For example, it says the knowledge is a power, and the model will to extract the text from this image to give us the output of the knowledge is a power. And after that, after the encoder, we'll go to the embedding layer, and here is where the semantic layer and the projector comes to play. And we will go to this part. I promise I will go through this try to go through this in an interesting way. So for the math part, we'll just to understand the nature of it. The first one is a distillation of knowledge. So for this formula, and it means for the semantic layer, it has a model which calls SigLIP. So SigLIP, and it is a quite high quality visual language pre-trained model. So basically what semantic layer does, it shares the vision transformer weight of the SigLIP. So it can preserve the language knowledge. And after that, it will be a projector path. So it is of this one. Yeah, it is of this one. So what this does is to ensure the stability and efficiency of the general output. And it is a basically more simple 2D patch embedding layer. And the semantic layer, because when we're dealing with the language knowledge, we will make things abstract. And we have the risk of losing a quite abundant amount of textures and the pixels of the picture. So the projector path can virally extract information from the VAE lattice, and it help us to make our output of the image very clear. Yeah, so it is about this dual path, about the semantic and the projector. And after that, our input will go to spatial temporal fusion. And here we can imagine the Show-O2 as a more backbone of the holistic architecture. For this, it deals with the causal and full attention. And it will also make the cross-modality integration and reasoning. After that, it will have the two heads. So the first one is the auto-regressive. It deals with the language, which is the LM head. And the second one is the flow matching. It deals with the image and the video, which is a flow head. And the final step is a text decomponizer and the 3D causal VAE decoder. And the right-hand side is an example. So it means like for user assess what's written on this image, please answer it in Chinese. And the system will reply by the Chinese of this picture, which is the knowledge is a power in English. And here is the image part. So the user says to draw a woman and says a be kind at the bottom of the picture. And also the third part is about from text to video. I think the next important thing about this paper is findings. It can be categorized into the quantitative and qualitative. And what it means is to compare, to have this huge table to compare it into the existing models. For example, the MU3 and also the SD3 5 large, and also all these types of models to showcase it is a quite light model of Show-O2. It only has 1.5 billion. So the 1.5 billion can actually perform better, for example, on the understanding of the multimodal, the MMLU, to compare to MU3, which has over 6 billion tokens. And it also has the second version, which is the 7 billion Show-O2. I think for this one, although it also shows it outperforms existing models, but the author discusses into its limitations because of the economic dimensions. So it's quite impractical for us to use a 7 billion now. And here is a qualitative one. The qualitative one, it shows the findings tells us about the outputs. There are mainly three types. First is a text to image. For example, we wanted to picture us a cat parrot, or we wanted to picture us a man or a woman. It will show us the image. And the second one is about the text to video. For example, here is a little girl with the blondie hair. And the third one is the image to video generation. It tells us about the input. Like we input the image, the cloud, and the person, and then it just like can move. Yeah, I think it is mainly about the findings. So about the limitations, I think there are two parts of it. The first one is about the text rendering, because the reason why it has limitations about text rendering is because the data, there is insufficient data input. For example, there are more data or images with little text and only a few data. There are the image with a lot of text. So text rendering is quite poor of the current Show-O2. So it also points to the future direction where we can have more data, where we balance the image with little or like with more text, so that our quality of the model can be higher for all of the types. So, and the second one I think is for the granularity or the details of our image. Let's say there is a picture consisting of a lot of soldiers or grass. So they are very subtle or nuanced objects. And for the objects that are farther away or like in a very small part of the picture, it is hard for the Show-O2 to capture the details of it. And it is the two limitations of it. And also, when I was reading, I also found it is there are some connected paper or like on similar topics. So the first one is about the transfusion. I will drop the link in the chat. So this is also another paper in this year's Neural IPS, and it is by, I think, if I'm not remember it wrong, it's from Meta. It tells us about transfusion. Oh, I saw one person ask, what was when? Oh, there's not asking. Okay, great. So like, yeah, so transfusion is one part of it. And another one is, I found one interesting point. It is flow matching. So the flow matching actually, it does not use the complicated diffusion, but like it uses the flow matching. And by having this formula, so it is about this one. So for having this formula, it actually uses a linear one. So the LM auto-regressive is quite discrete, but flow matching helps to deal with the continuous data. Show-O2 like supports in the 3D causal VAE space this type of continuous and linear path. Its generation, its logic of it is matched with LLM's causal attention. So it has a sense of aesthetic of the math, and it helps to prevent the diffusion model training. To like the researchers to deal with the noise schedule, and it helps the uh, model to deal with the model to deal with the video because video has a large scale, and so like it can now use a more cost-effective way of dealing the type of input as the video. Yeah, so this is the second one. And actually, like there is a paper in 2023, says by Lipman, and it says the flow matching for generative modeling. Yeah, so yeah, I think this is all I want to share for this paper. But I think, yeah, like if you have anything found interesting or like found similar topics that you found interesting, just please feel free to drop in the chat so that everyone can see more interesting papers. Oh, Frankie.
Yeah, can you hear me? I was wondering if you
Yeah.
can walk slowly through figure one. I just want to understand the architecture a little bit better.
Oh, sure. Yeah. For the architect, you mean this one, right?
Yeah.
Oh, sure. So for this one, we can break it down into four parts. The first is a text tokenizer and 3D causal VAE encoder. So this is the encoding phase. After that, we can see the embedding layer. The second important part of this is the dual path. So the dual path, it breaks down into semantic layer and projector. And
Oh,
third
sorry.
part is the show
Could I
out.
pause? Sorry, could I ask you slow down a little bit? So, what is the
Oh,
input here? Is the input what is written on this image, and then you actually have two things there, and you have a video, and you have some frames of a video plus somebody holding a bag. Is that what the input is, or what is the input here?
oh, sure. The input is uh, what's written on this image is just this sentence. So I think is, for example, we deal with the model. We are the user. You write it a prompt. The input is a prompt. What is written on this image? And plus we give, for example, the model, let's say in our daily conversation, instead of Show-O2, we'll just use ChatGPT as an example because it's more common in our daily life. We'll just give the model a picture, we will just assume we're getting this, which is the picture of a hand with a blue sky one, and we ask the model what is written on this image. So this is the input, and
Wh-
this is the
What is it?
first
What is a
part.
video? Is that a video stream on the right? The blue sky there. What is that on the right side? The
You mean this
frames.
one?
Yes. Yeah, the
Oh,
frames.
the
What is
frame is
that?
a video. Oh, it's a video, and
Okay.
for the
think
hand
you
one,
give,
it's
I
an
think
image.
you give it either or, an image or a video with text, and then input a
I was kind of
question of
confused.
what's.
So is it either or both, or I
I
don't
think
quite
it's either
understand.
or,
It's either
because
or.
the image has text on it, and the video has a series of images with text. So I think it can decode either or. I'm not sure though.
Okay, fine. What happens on that first box, text tokenizer and 3D VA encoder? What happens there on that first box?
So for the first part,
The first box, the top box, text tokenizer, 3D causal VA encoder. What happens there?
sure, I will try to send a mind map I built in our chat. So I think this might help to answer it. Mm, Give me a second. I'll find the material. Okay. Uh, while I was finding my mind map, I will see. Um, so for tokenizer, the model processed the text.
Yeah. Okay. And what about
Yeah,
the 3D causal VA encoder? What does that do?
yeah, sure. So, did I make it clear about the 3D? So, like for the three axis to make it into the three-dimensional one, does I make it clear about this concept?
What are the three dimensions?
Oh,
Time
sure.
and the XY. Go ahead. Yeah.
Yeah, so it is the spatial and the temporal. So the spatial, it is the x, y, and the temporal, it is the t. So together is x, y, t that constructs the causal. Sorry, the
Okay.
3D. Yeah.
Okay. Causal is because of temporal, right? Of the frames. And then what are
Yeah,
you
causal
doing with,
deals more
yeah,
with the temporal. Yeah.
yeah.
Going on.
Okay, fine. And then what are you doing like, or each frame? How are you breaking down each frame then on the tokenizer? Or I don't know, the first box. What's actually happening there on that first box?
This is a great question. Because I'm also like a beginner. So
Okay.
I will say like from my understanding, the causal, what I know about this paper is the causal nature is essential for the video because it ensures the model only looks at previous frames to predict the next. So yeah, but if anyone, I'm sure like there are a lot of people know better than I do. So like if you know that, please feel free to open your mic.
Yeah, do you mind if I share my screen and talk about the architecture a bit?
Yeah, sure.
Okay, so let me send a request to share screen because it says you're sharing screen.
Okay.
There we
So
go. Okay. Uh my screen share works? Can someone confirm they can see screen?
Are
Yeah.
you? Yes.
Okay, cool, cool, cool. So, two distinctions here. Just to recap a little bit, even before what they do, they kind of mentioned that there's two approaches that people do, right? There's like unified native models that are trained natively to have both text, image, multimodal understanding. Then there's these decoupled approaches, so stuff where you basically use an LLM backbone, then you have an vision encoder, and then you kind of merge them. So they're trying to go over this super unified approach, right? And their other big thing is that it supports video compared to their previous thing. So unified with video support. And then we go into how they do it. So there's four stages to this architecture. So this is kind of that framework. So obviously there's this one side that just takes in text. It's pretty straightforward, right? You have a text tokenizer, gets embedded. They have a fancy little attention mechanism here. I think it's called Omni-Attention that we can scroll into a bit later. And then, there's an LM head text decoding. That side is pretty straightforward. But the other side of this is kind of this flow for images and vision. I thought it's very interesting that they don't use auto-regressive image generation. So one of the things that they note here is that there's a few approaches. I thought the paper did a really good job at citing different papers. Um, Right now, there's basically two approaches. Uh, it was traditionally diffusion that was used for image and video generation, and diffusion was being scaled up. But some of the newer stuff this year is auto-regressive image generation, right? So you have an auto-regressive pixel by pixel generation, and there's slight attention differences there. To me, I assumed it makes more sense that when you do this sort of unified approach, you would want an auto-regressive model, right? You have auto-regression for images and auto-regression for text, and it seems like you can merge between those pretty easily. But instead, they're using a diffusion-based model. So how does it work? Basically, you have text that goes to embeddings. For images and videos, I think it's either or. You don't really get to pass in both. You can pass in an image or a video alongside it, and they talk about their tokenization here. Basically, they have these appended beginning of sentence for text, beginning of image, beginning of video. Then they have images or videos, which basically get embedded. They have VAEs that do this embedding. They have a few fun things that they do. Then they do this unified visual representation right here, which sort of it organizes the VAEs into like a proper representation, and then it has a sequence out of it that goes through attention. But that's part of what happens here. And then their other thing with this, like we talked about the SigLIP and this projection layer. This is the way that they do this. It's like part of their VAE. It's how they do this reconstruction. And there's like benefits to both. They talk about the ablation, but basically what happens, so you have your images and text, they go through this VAE that gives you, a latent representation. It's just like a unified representation. Then they do all this fun stuff to get it into the proper representation of a sequence. Then from there you do attention, and then it can go through the language model head or the flow head. But let's kind of break down a bit more. Sorry, I also like just read this, so I don't have the best understanding, but um, okay, you encode image, text, video into continuous embeddings and visual latents. These visual latents are processed through a dual path extraction for spatial, temporal, and fusion mechanisms constructed in a unified visual representations that are scalable for both then structured into a sequence. So this is that next step. So right here, they're talking about this, how they do this extraction. So you process the images and videos through 3D VAE, then to extract it into this sequence for the base length. Sorry, then structured into a sequence for the base language model. The way that they do this structuring is kind of this architecture here. So first, you have a 3D causal VAE. You pass your images or video into VAE. You get hidden basically a latent space representation. Then they have this dual path architecture. So there's these semantic layers that have high level features, and then you have these projection layers that kind of keep low level information. So that's what these two boxes are here. So after your VAE, you get a regular latent space representation of images. Then you have these two semantic and projection layers. They actually do an ablation towards the end about how important this two-step process is. They test whether you need this projection piece. Turns out you do, it still helps. From there, your output of these two is you get the spatial fusion, then you align it to sequential tokens. There's this SFT fusion mechanism. I don't know the exact architecture of what this stuff is, but they do reference the papers where they get it from. It's basically visual transformer blocks from SigLIP. That's what one of these is. The projection layer is something else. Um, I don't know the specifics about these, but they link the papers of what they get. So basically, you have a VAE, a little bit of noise. You go through these two different architectures. Then you have this spatial fusion step, this SFT. It's a fusion mechanism, and this is also where they do this embedding pre they add in these embedding tokens. So start a text, start a image, start a video, and all that stuff. Then from there, now you kind of have this unified. There's also a step where they concatenate the text and the image and interleave it with this. That's what this SFT step does. Um, don't exactly know how it works, but that's what's happening on the architecture. So from there, text was embedded normally. Images, video went through all these fun different architectures. Then they get concatenated, and we start adding in these, beginning of image, beginning of video, and all these tokens. From there, there's this little fusion thing that can decide which head we want to go to. So at this, there's an LLM with two heads, and they talk about how they train it too. One is the language head, one is the fusion head, the flow head. The flow head does images. They talk about in their training recipe how they have to freeze it. So like in stage one versus stage two, how they do it. So stage one is kind of freezing this LLM, and you're only training these. You freeze the LLM, you train this part, you train the projector, train the semantic layer, train the spatial fusions, train that. Stage two of this training is where you kind of train the language model for a merge and freeze the VAE stuff. You do that with high quality stuff. Then they talk about freezing this, scaling it up, and dropping it into a 7B. But that's kind of more concretely what's happening in this architecture. Sorry, it's not like the best explanation. I know I really skimmed over a lot of what is this SigLIP, what is this projection layer, but that's what they are. They talk about why they're important. Not so much about what each one does. Well, actually, they do say what each one does, right? So dual path architecture of semantic layers to extract high-level representations of rich semantic contextual information, and then the projector, which retains complete low-level information of visual latents. Specifically, semantic layers they share the same vision encoder of SigLIP, and then here's some fun math of how it works. But that's kind of what's happening here. I thought the other interesting step is kind of this reconstruction, right? So this STF step of spatial temporal fusion, that's where they can that's where they kind of unify it into a sequential step. And then they have that step of the model. This Omni-Attention, which can output to either head, the language model or the flow. This is all interesting because you're kind of merging auto-regressive text modeling. It's not all auto-regressive. And then the way that they let you interleave between the two of them is basically just in this step, you can add in these tokens. And then they even show like during generation stage, as the model as a language model auto-regressively outputs BOI, we switch over to the flow model and it starts generating an image till EOI is generated, So stuff like that starts to actually work. But also these are pretty small models. But yeah, I hope that kind of helps a bit. And then they do break down where all this stuff came from, right? So the language model component is Qwen 2.5, 1.5b. The VAE is the same VAE from WAN 2.1. So they're building off of the Qwen family here. They talk about the training stages, the context length, how many tokens, all that stuff here. I just don't think we didn't go into it that detail in that much detail. And then they also compare it to LLaVA-style adapters. There's an interesting section here about, like in the ablations, about these different stages, right? So, do they need this STF stage where you kind of reposition these two to be temporally consistent? Yes, you do. It helps. There's another ablation right after that about their architecture itself. So, where is this? Let me look at these ablations real quick. So Fusion helps. They talk about their two-stage approach. That was like one of their other takeaways. Their training, two stages of training. It's helpful if you only have one stage, it doesn't perform as well. Yeah, I'm not finding that section where they talked about not having the projector, but they definitely have it somewhere in here. But yeah, if we wanted to go more concretely into how this architecture worked, that's kind of a high level of what's going on here. I can pass it back, or we can talk about other stuff. Any other comments? I'll pull up the chat.
I have, I have, I have, I have a
Yeah,
question about the attention. So they say causal
yeah,
and full attention. So the idea is that the text during training, the text gets causal and the images get full attention because the images
yes,
are not. Okay, cool, cool.
yeah,
Cool.
yeah.
And do they also mention they mention the flow matching approach? Again, you mentioned why did not they try auto-regressive? Do they comment on why did not they approach it through auto-regressive generation?
Yeah,
Well,
I'll touch on both of those in a second. So
okay.
first, let's start with your Omni-Attention question, and also, anyone else feel free to chime in. Um, so they have a section on Omni-Attention. Where is this? We adopt this to let the sequence model, but I think there was a small section on this about why. Basically, it's causal attention over the whole sequence, full attention in the visual token box, just so that there's like global coherency. Where is it? Looking at my notes. Global- But yeah, I mean, basically, yeah, here it is, I think. Model's ability to interleave, generate coherent text. Um, No, they just talk about that. They use Omni-Attention. What Omni-Attention is basically causal attention. So, you have a masked auto-regressive objective, like you can only attend the previous tokens for the text model. So, that's the text part. The visual representation can see the whole image at once since it's not autoregressive. Um, that's just kind of how it's done. It's also so you can reference the whole image when decoding causally. So as you're predicting next token, you still have full attention over the entire image. Um, I read the Omni-Attention work a while ago. Basically, that was like one of their breakthroughs that you just keep vision uh, with full attention, and that works. I don't know if anyone has anything else to add on the Omni-Attention part before we talk about the other thing. Okay, I hope that's enough for Omni-Attention.
So another
Yeah,
question:
yeah.
do they add a LoRa or no?
No, no,
Oh
no,
wow. Okay.
Laura.
Okay.
Uh, yeah, there's not really a LoRa in here. It's just embedding space mapping. So you project to a latent space. This is kind of your merge step, but it's not a LoRa.
So
Um,
the causal and there is no language model internal step. It's just the embeddings layer goes through some attention layers which are trained from scratch, and then goes through LM head and flow head and then decodes.
well,
So
no, no, no. Two things. One, they talk about this in the limitations about how they do this on a very low budget. They mentioned that other models that approach this, they're basically trained from scratch and they don't have a budget for that, right? They're university students basically. So let me try to find it. So one of the big things that they do is that they talk about how they can do this without a strong budget. So um, they only have like tens of millions, hundreds of millions of images. So in doing this, they're not doing much training from scratch, right? They're using the backbone of different Quen models. They're taking a WAN video model and Quen language model, and the text generation and the image video generation understanding is done by kind of two separate models in this architecture. It's just merged and able to fluidly go between the two based on that STF like tokenization, adding in BOS stuff, But they're not necessarily training these embedding layers from scratch. Even those, they're kickstarted distillations that they swap in. So like there's little details there that I don't know how much detail we kind of went into.
Hey,
Yeah.
Vibu,
Okay. Thank you.
Yeah.
About the Omni-Attention, I was just reading a little bit more.
Mhm.
So it is like, is it normal attention for text? That is, you only causal, that is, you only look at the previous text
Yes.
for a particular text. Then there's like for visual, suppose you had like, you actually have tokens for a video, right? So that's also causal. That is, you only allowed to attend to previous frames of a particular video. And then there's visual to text, meaning that suppose that the text comes after the video, then it allows that text to attend to those previous videos frames. And then similarly, if you have video which comes after text, it allows a visual token ones to attend to previous text tokens. So it's actually all causal. I think the only difference is that uh, you maintain the causality within the video, you maintain the causality within the text, and depending on whether or not the video comes after text or text comes after video, you maintain that causality. So that's a
Okay.
kind of like how they do the Omni-Attention.
Makes sense. Makes sense. Thanks for clarifying there.
And then I
Um,
also looked up, oh, sorry, well, one more
yeah,
thing.
yeah, go
I
ahead, go ahead.
also
Yeah.
also looked up about like, how do they actually enforce semantic layers and projection layers, right? Because they're just blocks there. So reading a little bit more, the semantic layers is basically like a vision transformer, right? So of images, right? So basically, the task was, you have an image and you're gonna get an embedding for that image, right? Like in a vision transformer, right? The projector one, the one on blue, is basically taking patches of the image and say, hey, what is in this patch? So you can think of it as a smaller vision transformer, but only working on patches. For example, it may be able to tell you about the texture of this particular patch. So, if you think of it that way. So that's why the semantic layers can tell you about the overall image or, frame. And the projector one just tells you the more like patch level stuff. So that's a distinction between those two, the pink and the blue one. So think of the pink or salmon one, I'm sorry. Think of the salmon one as being more just a normal vision transformer, and think of the blue one also a vision transformer, but working on small patches. So it cannot tell you the whole thing about the image, but only about little sections of the image.
Yeah, the distinction they make there is about high level and low level information.
Yes, that's
So
right.
yeah, I think that's just a better way to understand it, right? Like little parts of the image as opposed to high level representation and low
Correct.
level. Yeah.
Now, I'm just wondering how they enforce it, like how do they enforce one is semantic and the other is projective. It's enforced by the spatial part, right? So one you have an embedding for the whole thing, and the other only have embedding limited to patches of the image.
Yeah, that's kind of what this vision block of a SigLIP is. And then for the patches, they break down like 2x2 patch embeddings. So they not only talk about it in the paper, but they do give all of the training code, the model, the weights, and all that. So if someone's diving deeper into this, like all that is pretty available. I thought
And
this
for the
fusion, yeah.
for the flow matching paper, I think the Pi 0.5 paper gives a very detailed explanation on like how they do flow matching. Of course, they do it in action space, not image and data, but the principle holds the same.
Yeah. And then like, yeah, this spatial temporal fusion, like it's concatenation of features. They have this whole thing of RSM norm with MLP layers, how they align video for fusion over time. All that's in there. Cool. I think you also asked about why they do um, diffusion plus language modeling and not auto-regressive. So I actually spent more time on the high level part of this paper, the intro where they want to also have this be a bit of a survey paper, right? They do a lot of really good linking. So they claim this new term, right? UMM, so unified multimodal models. Um, these can simultaneously understand and generate all this stuff. Um, we did another native multimodal fusion model earlier, like we did Flamingo, Lava, then we did a native one a while ago. So they talk about these two approaches to incorporating visual representations, right? There's the unified approach, which they do, which is papers like Chameleon. Then there's decoupled stuff where you have a VAE and all this stuff. But in this chart, they kind of talk about how stuff is done. So is it unified and how does it work? Then I think, yeah, so they talk here about the paradigm. So is it autoregressive? Is it autoregressive plus diffusion? Is it all autoregressive? There's one of these here, which made me note too, right? So where's theirs? I think I'm in the wrong table. Not. Yeah, here, there. So they're autoregressive plus diffusion. This one here does, it's unified, supports video. It's the same type of unified modeling, native and generative, but it's fully autoregressive. So I thought this was a fun one to look into. It seems like they do the same thing for diffusion. Then I looked into why. There was a reason for why they did it that I don't exactly remember, but let's see. It should be in here. Reconstructing this, VAE space, two-stage training. I'll point to it when I find it, or I'll just drop it in chat. But yeah, I don't want to just take over the screen while I find this. Did anyone else have any other comments, thoughts on this paper, or should I pass it back, or should we just leave it up? I guess while we're quiet, there's also that section about in their training. Typically, LLMs and LMMs are trained from scratch. Um, this process relies on web scale, high quality text corpora, which is prohibitively expensive to collect. So that's why one of their big things in this paper is this two-stage recipe, right? You can retain language knowledge and develop visual reasoning. They talk about other papers that or other models that either lose their language model capability as you train, and then same with the opposite. And then this is kind of the breakdown of their data sets. It's not that much data. Image text pairs, these sum up to under 100 million. Same with video data, it's under 100 million. There's not that much data here. And then they talk about in each stage what they're freezing. So yeah. Cool. Any other cost of training? I don't think they talk about the cost. Oh, they do right there, right there. My thing is frozen. One sec. Let's see. In training for 7B, they do talk about scaling it up. We do not include interleave video. The whole training process of our 7B takes approximately 2.5 days and using 128 H100 GPUs. So not many GPU hours. And this is their scaled up. Their primary model is the 1.5B. They talk about scaling it up to a 7B and doing that, the whole training process, this is what, like less than 10,000 H100 hours. So pretty small, pretty cheap. Total, like roughly 100 million multimodal samples. They do talk about for this training data, rewriting it and augmenting it. So like images are recaptioned by LMMs, stuff like that. Yeah. They talk about the training steps, iterations, learning rate, all that stuff. But point being, this is not that expensive. I think this training process roughly takes 1.5 days using 64 H100s. So not much. I don't know if this is talking about the whole thing or that half, but scale of training is not that high. Okay, more comments, thoughts, concerns? I think the interleaving is very interesting. I think it's another thing to note that they don't use a reasoning model. Like the 1.5B Quen 2.5 that they build off of isn't a reasoning model. A fun thing about Omni models is being able to interleave your reasoning with multimodalities, right? Like right now, we don't know how to make diffusion models reason per se, right? Like we can't reason in the diffusion space. So when you have stuff like this, if you can, I don't know, reason before you do your generation, or you can reason, generate, reason again, that stuff's pretty promising. That's a bit more why ChatGPT image gen switched to auto-regressive reasoning. That lets them reason in the middle of auto-regressive generation. That's some fun stuff.
Hi. Yeah, that's the Uber for Jasmine, right? Yeah, awesome. So we need to move a few stuff.
Somebody's getting an Uber.
I muted the guy.
Okay.
Sorry, I gotta mute this. Yeah.
He's
Yep.
unmuted. Okay. Anyway, should I pass back? I feel like I've been screen sharing for a while. Or does anyone else have any other stuff, comments?
Can I ask a question? Or it's maybe a very naive comment. I'm not too familiar with the field. I'm just struck, by the name natively multimodal. And when I followed your presentations, and it seems like so you have the embedding on top, and then the processing gets split into two streams, right? On the left stream, basically, the way I understood you, the left stream basically does the text processing, and the right-hand side stream does the audio video processing. And so you get all these the processing done on that level, and then you combine it again at this Show-O2 attention layer. So my question, I guess, is like how deep is the native integration really? How much of the processing is really combining the two versus just, okay, we do the embedding and then we do separate processing and then we can do intention on the outputs in latent space, basically.
Yeah, it's a good question, honestly. Like it felt a bit like a LLaVA-style adapter, right? You freeze the weights of the language model, you do a bit of joint embedding training, and then you just generate one. The difference here isn't really about understanding both, it's about this sort of internal router as well, right? So you can also generate out images and text and video, and you can interleave in between them. So this shared space lets you join between the two, right? Typically, when you just have embedding space match, you can use that for generating one modality, but often not both, right? But yeah, I think it's a very fair, valid question. Does anyone else have other comments, takes?
I don't have a question about this paper in particular, but since you mentioned the unified multimodal, like basically that phrase, I've just been generally curious about how that compares to just multimodal models and like vision language models, and then can you like give a high level of how just uh, like transform basically like LLMs, vision language models, and then multimodal models, and then finally unified multimodal models.
Yeah,
Oh, they actually have it there?
they have the full section right there. It's section 2. We
Awesome.
can
Yeah,
we
I
can
guess I
kind
can
of,
read that.
yeah. I mean, we can also just do a quick overview, right? I'm sure it's on a lot of people's minds. So, um, LMMs, large multimodal models, what they basically do is use a vision encoder, like we just talked about. You align it to the LLM space, right? Um, they're kind of encoder free. Um, they just align images to the LLM space. And the problem there is they kind of lag in performance, right? Um, the like you really need high quality instruct data, but they kind of they lag in performance. They aim to directly align raw visual features with LLM embeddings. There's some fun
Mm.
stuff that starts to happen where yeah, people try to do encoder free models. Often fall behind models that utilized image text aligned visual features in terms of performance. So yeah, you don't really have, you just need good matching, but yeah, not that good. Visual generative
Mm.
models, this is like, this is just diffusion or auto-regressive. This is not language backbone, right? This is just, you do the opposite. You train a really good image gen or video gen model that can understand a caption or a query, right? But I can't pass in like a book. These are just outputting only images. There's two approaches. So diffusion is noise based. You denoise, you start at random pixels and then you denoise to whatever you want, and it's trained on like image text pairs, right? So really high
Mm.
quality image descriptions, and you're denoising that to just generate images. These won't do the LLM style reasoning backbone pre-training, right? These are just mostly image generation. There are some
Mm.
hybrids. They try to combine these architectures and do autoregressive stuff. This is some of the newer things. Um,
Mm.
UMMs are kind of this all-in-one modality thing that they talk about. This is what their thing is. Um, yeah, so it's
Okay.
native unified is what they call it, versus like assembling tailored stuff. The Chameleon paper is actually a really good original version of this that people should read. I think we covered it in Paper Club like a year ago.
Cool, thanks.
Are the outputs from both stream of embeddings pre-attention just concatenated? There's some concatenation that they do. Um, let's see. This STF stage in this spatial temporal fusion concatenates these two, and then it also aligns this stuff. There's a section on it. They fuse it. It's called fusion, spatial temporal fusion. For video, fusion aligns over time. They prepend timestamps. Yeah, you can read more about that section. But they do mostly just concatenate with interleaved additional tokens. Then there's the Omni-Attention over this. Cool. Other comments? I guess someone asked how this is different than the high level like merge embedding space of a lava style model where you're kind of just doing all things in one modality and then you're outputting text. I think I have a better answer to that, right? So when you do this step of just match embedding latent space and then you output text, what traditionally lava style models do is that the output is fixed, right? You end out at an auto-regressive model and you have to output text. The difference here is that they've done this fusion step and you can go between any modality, right? So you can do video decoding, you can do interleave generation of like video image text, you can pass in uh paper and get a full video out, right? It's also that you can swap between all these modalities. The lava style approach only lets you read one modality or read multiple, and then you have to output to one. Here, you're outputting to any modality as well. So it's not just the match of embedding space for the encoder, it's also operationally having that joint attention over the two and being able to output in both. And then also, they're doing this with diffusion. So those two embedding spaces are kind of different. Cool. Should we call it here? Do we have any other stuff? Ted shared a blurb. A high-level concept that I've bumped into is that for multimodal LLMs, you can either do cross-attention with visual inputs, or you can insert visual tokens into context. For most models like Show-O2, which use visual tokens, these tokens increase the context length. For video that can grow fast, this is why multimodal LLMs tend to have weak vision encoders, which produce relatively few tokens, and this limits visual understanding. Yeah, that's true. Vision tokens increase context fast. If you guys read the DeepSeek OCR paper, it's an interesting one. It goes kind of the other way. It shows that visual tokens can be used as embeddings to save context length and are more space efficient. But that's directly trying to solve, can we compress 128,000 tokens more efficiently? You can use visual embeddings. But anyway, good note there. Cool. Well, Happy New Year, guys. We will have more papers soon. Very exciting stuff.
Happy New Year.
Happy New Year.
And thank you so much for presenting, by the way.
Yes, thanks, Sia.
Yeah, happy new.
Happy New Year.
Everyone,
Thanks.
take care.
Cool. We'll see you guys next week.
Everyone, see you next week. Bye.
Thank you.
All right.